Down to section 6.5, graphs of the tangent, cotangent, cosecant, and secant functions. So here we're just going to look over the basic parent graphs, identify some key features, and then we'll go over 4 examples total, one for each of the new functions that we're going to be graphing. So to begin with, let's look at y equals tangent of x. Notice that tangent has vertical asymptotes, and the vertical asymptotes, the first one that's notable that we usually graph is at x equals pi over 2, and then the other one is at x equals negative pi over 2. Now, the period for tangent is just pi. We mentioned that earlier a couple sections ago, and you can see that the distance between the two vertical asymptotes is pi, and so the tangent graph repeats every pi. That's why its period is pi. Notice the graph of tangent will have a vertical asymptote everywhere tangent is undefined. So remember, since tangent is equal to sine of x over cosine of x, everywhere that cosine is 0 is where the graph will have a vertical asymptote. So think about it. Cosine is 0 at pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2, so on and so forth. Okay, and then the other two key points to plot are at pi over 4 comma 1, which you can see right here, and at negative pi over 4, negative 1. Okay, so when you're graphing tangent, you again will include 5 like little key points on your graph. The step is still going to be the period divided by 4. The asymptote is going to be one of them. This value here is the next one. It goes through 0, 0. Here's number 4, and then the asymptote is the 5th one. And typically 1 period is enough to graph. The shape of tangent, it looks like x cubed, but we know x cubed doesn't have any asymptotes, right? Y equals x cubed, the domain and range are all real numbers. But this has a similar shape to it, if that helps you remember. Okay, now moving on to cotangent of x. The only difference is that the asymptotes are in different places because, of course, cotangent x is cosine x over sine x. So in this case, everywhere that sine is 0, cotangent is undefined. So that's where this graph will have vertical asymptotes. So if we think about it, where is sine 0? Imagine your unit circle. That would be at 0, pi, 2 pi, so on and so forth. So the first asymptote is actually at the y-axis. Notice for tangent, it's the other way around. It crosses through the origin, and then the asymptotes are split evenly on either side of it. Where in this case, the starting point for cotangent, the asymptote is at the y-axis. Also, it looks like tangent being reflected, right? It looks like a negative x cubed, so it's a decreasing function. And then the other key points are the same. So you would have pi over 4, 1, and then 3 pi over 4, negative 1. And then halfway through, the period is still pi. This distance here is pi between the asymptotes. And then halfway through is where it crosses the origin. Okay? So that's pretty much it. Just remember the period is pi on tangent and cotangent, and the process will proceed pretty similar with graphing these as the others. You just got to include those asymptotes. All right, moving on to cosecant. Now let's think about how to come up with the graph. The cosecant graph is shown here in blue. Okay, cosecant x is 1 over sine x, right? It's the reciprocal function for sine x. So let's think about this. And I actually want you guys to recall when we graphed rational functions, okay? When we were graphing rational functions, we knew that we could find the equations of the vertical asymptotes by identifying when the denominator was 0, right? So what we do when we graph cosecant is we first actually graph sine of x. This is sine of x here. And everywhere that sine of x is 0, for example right here, the graph of cosecant will have a vertical asymptote. So notice how at all the zeros for sine x, we have a vertical asymptote. Yeah, this was 1 too. You just can't see it because it's on top of the y-axis, but it's there. Okay, so the process is you would graph sine x first. Everywhere that sine x has a 0 is where cosecant x would have a vertical asymptote. And then the other nice points to plot are basically everywhere that sine is 1 or -1. Because if you'll see here, cosecant is 1 over sine x. So 1 over 1, excuse me, is still 1, and 1 over -1 is also still -1. So all the max and min values they have in common. And then the graph of cosecant x, basically, I mean, they're not parabolas, but they kind of look like them. They're little smashed parabolas between the asymptotes here. And they always go away from the x-axis, right? They will never equal 0. They always go away from the x-axis. Notice here the numerator is 1, so cosecant can never equal 0. And then secant x, very similar process. Just remember secant x is 1 over cosine x. So then basically everywhere cosine x has a 0, the graph of secant x will have an asymptote. And then they also share in common all the max and min values, okay? For both of these, the period is 2 pi, because think about it. They're based off of the graph of sine and cosine, and the period for those two graphs are 2 pi. So that's why secant and cosecant also have a period of 2 pi. All right, so let's just dive right in. Let's graph a secant graph. Why not? So the directions say graph the function, label key points, so that'll be 5 of them, and show at least 2 cycles. Oh, then that's 9 key points. Okay, we're really going for it with this one. That's fine. And then use the graph to determine the domain and the range of each function. Okay, so what we're gonna do first is actually graph cosine, okay, of pi over 2x, okay? Now notice here for cosine, that means the amplitude, which is the absolute value of -3, is 3. Now secant doesn't have an amplitude because we know the graph of secant looks like this, right? So it's not bounded, but cosine and sine, those graphs they have an amplitude. The -3 also means that it's been reflected, right? About the x-axis. And there's been a change in the period, right? So the period would be 2 pi over 2. The pi's cancel. That 2 in the denominator flips to the numerator, so the period is 4. That means the step is the period divided by 4, which would be 1. Okay, so that's actually kind of nice. So here, let's start labeling. Here's my x-axis, here's my y-axis. Since I have to go all the way up to 3 and -3, well, let's just call this 3. How's that sound? Okay, and the step is 1. So 1, 2, 3, 4. There's 1 period. And then since the problem asks for 2 cycles, instead of going 5, 6, 7, 8, I'm going to go backwards to the left. So we'll have, oh, don't forget 0, and then -1, -2, -3, -4. Okay? Good. Now I'm going to graph cosine. Remember, cosine typically at 0 starts up at the top at its max value, but in this case, since we have a reflection, it's going to start down here at -3. Then it's going to go to 0, back up to 3, back to 0, down to -3, and then I'm going to keep going on the other side. So at x equals -1, it's back to 0, then up at 3, back to 0, down at -3. So this is the graph. I'm just going to draw it dashed for cosine, because remember, that's not what the problem asked. So this I'm just going to use as a guide, okay? Now, what I want to start with is drawing the vertical asymptotes. Everywhere my cosine graph crosses the x-axis, everywhere I have an x-intercept, there's going to be a vertical asymptote. So one of them, another one right here, another one right here, and another one right here. Okay, perfect. And then when you draw your little smashed parabolas for the graph of secant x, let me switch colors because the final answer is the graph of secant. Remember, they're going to have in common the max and min value. So I'm going to take this peak here and draw what resembles a parabola going away from the x-axis, always away. So this one, they share in common that -3 and then draw it going away from the x-axis. And then same thing over here. Away, away, away. Technically, I have another little half a guy right here, yeah? And a little half right here. Don't forget them if we're going to draw 2 complete cycles. Okay, the graph looks good. Now let's list out the domain and the range. Now we have to be careful. So the domain, let's think about how we would write the domain for rational functions, right? Because we had vertical asymptotes then. So we would write it out as all x's such that x does not equal, and then we would list the restrictions. Can I list every possible restriction for secant here? Well, no, because there's infinitely many, right? What are the restrictions in the domain? They're everywhere we have a vertical asymptote. So the cleanest way to write it out is as follows. Identify where the first positive vertical asymptote is. In this case, it's at x equals 1, right? So that's a restriction. So my domain is all x's such that x doesn't equal 1 plus how often do they repeat, or how long does it take until we run into another restriction, another vertical asymptote? Well, look at the distance here. The equation of the next vertical asymptote is x equals 3, okay? So that's a distance of 2. And then we would know the next one would be at x equals 5, right? And you could also go the other way. At x equals -1, that's also a distance of 2. At x equals -3, and so on and so forth. So you have to keep adding or subtracting 2 in order to list out all the restrictions. So I say x cannot equal 1 plus 2 times k, where k is an element of or belongs to the set of integers. Okay, so just to remind you, k is an element of, or that belongs to, and z is the set of integers. So integers can be positive or negative, right? So basically I'm saying I can take 1 plus 2 times 1, 2 times 2, 2 times 3, 2 times -1. I can add or subtract any multiple of 2, and that's going to exhaust my list of restrictions or asymptotes. Okay? Good. Ooh. Now the range. The range won't be so terrible. So the range, we have to write it in 2 parts. Easiest thing is to do interval notation. Notice that these parabolas, or what look like parabolas, go down forever, and the highest they'll ever be is -3, right? And then on the other side, they go up forever, and the smallest value they'll take on is +3. But there's nothing in between -3 or +3, so we have to skip over that part. So the range is going to go from -infinity to -3, include -3, union +3 to infinity. And if you wanted to write this in set builder notation instead, you could write y such that y is less than or equal to -3, or y is greater than or equal to 3. Either one is fine. Okay, we got that one. How are we feeling? Let's move on to an example with cotangent this time. Okay, so we have y equals 2 cotangent of x minus 1. So a couple transformations I notice here. First one is this is going to be a vertical stretch by 2. And then this also shifts the graph down 1, correct? Okay, and then recall the period for cotangent is pi. And in this case, it hasn't been changed, right? I don't have a coefficient on x, so the period's still pi. The step is always the period divided by 4. All right, and in this case, they want 2 periods. So the vertical asymptote, you just have to remember this. For cotangent, it starts at the y-axis. Okay, and then let's go ahead and label. Each of these tick marks can be a step. Why not? We got room. So here's going to be pi over 4. Add another pi over 4. That's 2 pi over 4. So that's pi over 2. Then 3 pi over 4. And then 4 pi over 4, which is pi. And now we've completed one period. So that's where the next asymptote is going to go. And then let's go the other way. Let's label x and y. So the other way, here's 0, then negative pi over 4, negative 2 pi over 4, which is negative pi over 2, negative 3 pi over 4, and then negative pi. All right. Good. Okay, and then we'll label here, this will be, I'm trying to think. Let's do 1, 2, 3, 4, and then this will be negative 2, negative 4. Okay, lovely. Now, other thing to keep in mind, normally cotangent, when we would graph at pi over 4 and 3 pi over 4, those would take on the values of 1 and negative 1. But in this case, since we have a vertical stretch by 2, they would be at 2 and negative 2. But then don't forget, we also have to shift those down 1. So those are going to shift down 1 unit. And I'm going to plot, let's do blue. Pi over 4, 1. And 3 pi over 4, negative 3. Okay. And then typically halfway between the asymptotes is where it crosses the x-axis. So that would be at pi over 2, but we're shifting down 1 unit. So that would be at pi over 2, negative 1. And then just make it resemble something that looks like negative x cubed, like a decreasing function with that little wiggle in it. Don't draw it too straight. And then same thing here. So quarter of the way through, it's going to be at positive 1, at negative pi over 2, negative 1, and then at negative pi over 4, it's going to be at negative 3. All right. Don't forget to put arrows. Draw a nice smooth curve. Beautiful. So that's 2 complete cycles. Now let's list the domain and range. Again, for the domain, we're going to have infinitely many restrictions, so we have to figure out how to write it properly. So the domain is all x's such that x cannot equal, well, what's the equation of the first positive asymptote that you see? Well, it's pi, but really right here at x equals 0, we have an asymptote, right? And it takes the period pi to repeat. So you would say x cannot equal 0 plus pi k, but you don't need to put 0 plus anything, right? 0 plus is worthless. So pi k, where k is an integer. And then the range here is actually pretty straightforward. Can you tell just by looking? It's going to be all real numbers. Or you could write negative infinity to infinity. Okay, looks good. Shall we keep going? Do we feel ready? Okay. Next is y equals cosecant of 3 pi over 2 times x. So again, we're going to start off by graphing sine, okay? And then there's been no stretches, no reflection, no vertical shifting. The only thing that's happened is the period's been adjusted. So that's not too terrible. So let's see here. The period is going to be 2 pi over 3 pi over 2. So the pi's are going to cancel out, and this is going to give me 4 over 3. Okay, now to get the step, I take the period and I divide by 4. When your period is a fraction and you're dividing by 4, it's easier to think of multiplying by 1/4. It's the same thing, but then you can see that the step is going to be 1/3. Okay, so let's go ahead and start graphing. So here's x, here's y. I'll label this 1, negative 1. So we'll start at 0. The step is 1/3. So 1/3, 2/3, 3/3, which is 1, and then 4/3. That's 1 period. And then I'll go to the left. So negative 1/3, negative 2/3, negative 3/3, which is negative 1, and then negative 4/3. All right. And this time, remember, cosecant is the reciprocal function of sine. Okay. So sine at 0 starts at 0. Then it goes up, back to 0, down, back to 0. And then on the other side, it'll go down to negative 1, back to 0, up, back to 0. Okay? Now it's up to you. If you don't even want to draw the dashed lines in for sine and you want to just jump straight to drawing the asymptotes because you can already see where the zeros are, that's fine. I'm not going to skip any steps though, just because I know everyone's at a different place. So here's the graph of sine. And then now let's begin by drawing the vertical asymptote. So everywhere this graph has an x-intercept, we're going to draw the vertical asymptote because that's everywhere cosecant would be undefined. So vertical asymptote right here at -4/3, another one at -2/3. Don't forget the y-axis is a vertical asymptote. I always like to draw a little bit above and below to remind myself. 2/3 is another vertical asymptote. And so is 4/3. Okay. And then the actual graph of cosecant, it's going to share in common all the max and min points, right, on the sine wave. And then remember, it looks like little smashed parabolas that always go away from the x-axis. Okay. Looks good. Great. Now let's list the domain and range. Okay, so the domain is all x's such that x cannot equal. Well, notice we have our first vertical asymptote at x equals 0, and then the next one is at x equals 2/3. So it takes 2/3 units, right, for it to repeat. And then again at x equals 4/3. So you keep adding or subtracting 2/3. So we say x cannot equal any multiple of 2/3 or 2/3 k, where k is an integer. Okay, and then for the range, the graph goes all the way down to -infinity up until -1. Yes. And then you have to jump over the part in the middle. So you say union +1 until +infinity. Okay. How are we doing? I promised you one example of each, and we already did a cotangent. So I'm taking some liberties. We're changing this to tangent, guys, okay? Hang in there. All right, so this one has a lot going on. The 3 means there's been a vertical stretch. Remember, tangent, cotangent, all of these 4 graphs we're considering in this section, they don't have an amplitude because they're unbounded. What else is going on here? We've got a vertical shift down. And then this 1/2 in front of the x, that's going to affect the period. So the period here, remember, originally tangent's period is just pi. So I'm going to take pi and divide it by 1/2. So not 2 pi because it's tangent. So pi divided by 1/2, that's the same as pi times 2. So the period is 2 pi now, which means the step is going to be 2 pi over 4, which is pi over 2. Okay, so let's start graphing. Let's label our axes. Here's x, here's y. The step is pi over 2. So I'll call this pi over 2. This is pi. And then negative pi over 2, negative pi. And remember, for tangent, typically it goes through the origin, right? And then the asymptotes are split evenly on either side. But we have a vertical stretch by 3 and the graph is shifted down 2 units. So this is going to shift. Let's label everything. Maybe we'll label by 2s, yeah? So this is going to be 2, 3, 4, 5, and then -2, -4, -5. Okay, so 0, if it gets vertically stretched, that won't move, but if it shifts down 2 units, then yes, now it'll cross through here. And then pi over 2 typically crosses, let me show you the transformations. Pi over 2 typically crosses at 1, right, a quarter of the way. But then we're vertically stretching, we're multiplying by 3, so then that would move up to 3. But then we're shifting down 2, So guess what, guys? It goes back to 1, right? If it's at 3 minus 2, that's back to 1. And then lastly, let's see here. So at negative pi over 2, it would go through negative 1, but then it would get stretched to negative 3, and then it goes down 2, so it's at negative 5. All right, that was a lot. Okay, this one's all stretched out. Looks good. So that's 1 period. They wanted 2 periods. So it's up to us. Which way do we want to go? Let's go to the right. And you can check that you did it right because look at the distance here. So this is 1. 1 to negative 2. Is that 3 units? And then is this another 3 units? It is. And it should match the coefficient right there on tangent. So that way you know that you did all the transformations properly. Okay, so let's keep adding the step of pi over 2. So pi right here, that's 2 pi over 2. So this is going to be 5 pi over 2, 6 pi over 2, which is, no, what am I doing? This is 3 pi over 2. I'm sorry. 2 pi over 2, now this is 3 pi over 2. 4 pi over 2, which is 2 pi. 5 pi over 2. And then now we have our 6 pi over 2, which is 3 pi. Okay. And that's where we have the other vertical asymptote. And then you can just kind of match the other points. So halfway through at 2 pi, it's going to have a y value of negative 2. Just copy over everything. At 3 pi over 2 will be at negative 5. And then at 5 pi over 2 will be at positive 1. Okay. Good, good, good. So now let's list out the domain and range. So the domain is going to be all x's such that x does not equal, well, the first positive equation for an asymptote I see is at x equals pi, and then the next one is at x equals 3 pi. So the distance between these two values is 2 pi, right? The period. So x cannot equal pi plus 2 pi k, where k is an integer. And then the range is all real numbers, or you could say negative infinity to infinity and beyond. Okay, so that concludes section 6.5. We only have one more section in chapter 6, so stay tuned.